Okay, where we're at, we're talking about equilibrium. And so equilibrium, it deals, so when you have a chemical reaction, so if you look at this equation here, carbon monoxide and equilibrium of carbon dioxide and carbon. So you would think that the equilibrium constant, it's products over reactants. So concentration of carbon dioxide, concentration of carbon divided by the concentration of carbon monoxide squared. So, but what can you tell me about a solid? Well, before that, does anybody know the concentration of water? Liquid water. It's 56 molar. So it's, so moles per liter, it's 1,000 grams divided by 18 grams per mole. So it's 55.5, the Z bar, 55.56. Depends on how many sig figs you want to use. So that's the concentration of water. Does the concentration of water, this container has water in it, so does the concentration of pure water, does it change? And the answer is no, right? So liquids tend to be incompressible, in some ways even more than solids. So so liquids are incompressible, so that means that their volume doesn't change that much, which means the concentration of liquid water is not going to change. Doesn't matter if you have a drop, and it's an intrinsic quality, right? Doesn't matter if you have Lake Tahoe, if you have a drop, or if you have a liter, it's the same. So it's a constant, and that means when you have an equilibrium constant, that when you deal with something like a solid, it's the same with solids, it's going to be, the concentrations are not going to change. So you remove the concentration of the solid and or the liquid from that, and then you have the equilibrium constant described without that. So, okay. Other questions? All right, moving on, next concept. And this is something that we're going to do for the next couple chapters. So then it's called an ice chart. So surprise, surprise. So an ice chart, and it's I stands for initial, C stands for change, E stands for equilibrium. So look at this problem. Consider this reaction. Carbon monoxide plus 2 hydrogens makes methanol. Initial concentration has carbon monoxide 0.5 molar, hydrogen at 1 molar. At equilibrium, the carbon monoxide is 0.15 molar. What's the value of the equilibrium constant? So let me put in the given information. So first of all, let me show you this chart. I've gone ahead and written the equation, right? So that's a chemical equation, balanced chemical equation. And underneath them, here's the concentration of each of the species. So let's put in the information, the known information. Let's see here. Initially, carbon monoxide is 0.5 molar, hydrogen is 1 molar. And then equilibrium, carbon monoxide is 0.15. Does that say equilibrium? Okay, so written there in blue, if you can see what I've just written, that's the given information. So now let's infer some information. So initially, we can assume then that the methanol concentration is 0 because I didn't mention it, right? So if I came into class today and I said, I have a $5 bill and 2 $1 bills on my wallet, and then I ask you, how many $100 bills do I have? If I come in and said, I have this much money in my wallet, or this type of bills in my wallet, and if I don't announce them, then you can assume it's 0. So not announcing the methanol, initially I have this, I'm not listed the other ones, you can assume the other one is 0. So the other thing is, if we have initially half molar and an equilibrium, we have 0.15 molar, we can then say that, you know, what's happening is we're losing 0.35. So the change, so I'm gonna, I guess no one's on Zoom, but even though it's recorded. So initially, we start off with 0.5, and we end up with 15 at the end. So that means that the change between this is negative 0.35. It's the carbon monoxide is losing 0.35 molars. So what does that mean? So I'm going to go on, I can infer more. The hydrogen starts off with 1, and there's a 2 here. So hydrogen's going to lose 0.7, right? So because hydrogen is consumed twice as fast, and reactants are consumed, products are generated, and we have, for every 1 part of reaction going forward, we gain 1 part of methanol. So methanol is going to gain by 0.35. So does everybody see my logic so far? And I'm going to change colors just to so this is inferred. Then hydrogen is 0.3, methanol is 0.35, because we're just adding these lines. So we're just adding those lines together to that. So I is initial, C is change, E is equilibrium. So now we have these values, and we can plug them in. The equilibrium constant then is products 0.35 over reactants 0.15, 0.3 squared for hydrogen. And if you put that in your handy dandy calculator, you get, why did that just disappear? 26. Okay. So recap with this one, and this, the whole point of this example, we're going to go over more complicated ones very soon, is the ice chart. So you don't have to use this if you don't want to. Actually, I was taught chemistry not using the ice chart. I was taught to put in the equations and just, you know, so equilibrium values, just figure out the equilibrium values and put it in. So I wasn't taught this way, but I think this way makes more sense. So rather than they see it as a, you know, an algebra word problem. So initial change equilibrium. So from the problem, we can, the original information, the given information is we initially have 0.5 molar carbon monoxide, 1 molar hydrogen, and at equilibrium, the carbon monoxide concentration is 0.15 molar. So what we can infer from that is that if we have reactants and no products are listed, that we just have an empty vessel and we're throwing in reactants and we have no products. So the initial concentration of the methanol product is 0. So, but from the fact that carbon monoxide starts at 0.5 molar and ends up at 0.15 molar, we know that we lose 0.35 molar of carbon monoxide. And it's a 1-to-1 ratio for the carbon monoxide in the whole equation. So sometimes this 0.35 is referred to as the extent of reaction. So we have the reaction going forward, the extent of reaction going forward is 0.35. And hydrogen is going to lose 0.7 molar because there's 2 hydrogens in the balanced chemical equation, which means that the hydrogen is going to be consumed at the rate of 2 times the extent of reaction. And so we lose 2 extent of reactions of hydrogen, and then we gain 1 extent of reaction of methanol. And then we compare the extent of reaction to the initial values. And then from that, we get 0.15 molar carbon monoxide, 0.3 molar hydrogen, 0.35 molar methanol. And then we look at the equilibrium constant, products over reactants raised to their powers, or concentration of methanol over carbon monoxide times hydrogen squared, plug in the values, and we get an equilibrium constant value of 26. So questions with this?
How did you originally get
0.35. So think of it like this equation. So think of it as ham plus 2 pieces of bread, equilibrium with a ham sandwich, right? So if for every, right, so, and instead of this, let's say we have 50 pieces of ham and I end up with 15 pieces of ham, and we have 100 pieces of bread and no ham sandwiches. So, which means that my ham, I'm losing minus 35 pieces of ham, and then, which means the extent of this reaction is 35 ham sandwiches. So if I'm making 35 ham sandwiches, I'm losing 70 pieces of bread and I'm gaining 35 ham sandwiches. So it's the whole idea of a reaction. You have an extent of a reaction. And I know I'm using a colloquial example with ham sandwiches, right? But for when the reactants are consumed, the products are generated. Okay. So we have negative reactants, positive products.
So if it was 2 ham sandwiches, then you would gain a double.
Yes. Yes, and
70.
yeah, exactly. Although a bit of caution with that, going forward, reactions, since they can go both ways. Sometimes we write the reactions and then it actually shifts to the left towards the reactants, and then you'd have to change the extent of reaction based on where the reaction is going. So, but that's for the future. But for your logic right now is sound. Other questions? Okay. All right. So as stated, we're going to predict the direction of a reaction. So not everything is always at equilibrium. So, but part of this, and actually this is one of the things that I hope you can get from chemistry going forward. Like, I guess I'm biased because, you know, I'm a chemistry teacher, but many people don't know their basic chemistry. And you can actually, if you understand basic chemistry, you can sound really smart, you know, I mean, and one of them is using equilibrium concepts to predict changes. And this is certainly true in economics too. I'm like, we'll talk about this a little later, something called Le Chatelier's principle. But building up to that, we have this idea of reaction quotients. So predicting the direction of a reaction. So here's the generic chemical equation, and the reaction quotient, QC for concentration, it's just like the equilibrium constant, right? So products over reactants raise their powers, and the QP, the quotient in respect to pressures for gases, same idea, but it's just at any given time. So the reaction quotient is equal to the equilibrium constant at equilibrium, because everything's at equilibrium concentrations. But Q is the reaction quotient is any given time. So it's not just at equilibrium. So at equilibrium, Q equals K. And so the other thing for me, I don't memorize a lot of some things in chemistry. I have to figure it out. And so for me, I always kind of logic my way through it. I don't off the top of my head remember if Q is bigger or smaller, how that relates to the chemical reaction. So let me think. If, let's say Q is too big. If Q is too big, so we're going towards equilibrium constant, say Q is a big number, that means that the numerator, the fraction and the numerator of the fraction, the top number is too big and the bottom number is too small. The top number is too big, that means we have too many products. If we have too many products, that means the reaction is going to shift towards the reactants to shift left. So if Q is too small, say Q is too small, that means the top number is too small and the bottom number is too big. So the numerator is too big, denominator is too small. Wait a second. Did I say? Which one am I going to? I'm sorry, if it's small, that means the top number is too small, the bottom number is too big. That means we're going to shift right towards the products because the bottom number needs to get smaller, the top number needs to get bigger. So, and a couple other things, for many of these problems, you'll see if you have only reactants, that means that there's 0 over some number. 0 over some number is always 0. If we have only products, that means we have top number, that's a number, bottom number is 0, close to 0. That means that the reaction quotient is infinity. So, and of course that's easy. There's no number smaller than 0. Well, I mean, at least absolute values, if you will. There's no number, whole number, or whatever, or like positive number smaller than 0. So that means if Q is 0, then you're going to shift right towards products. And there's no number smaller than infinity. If you have infinity for Q, you're going to shift left towards reactants. So those are always easy. So questions with that one? And I'll show this in some problems. And if you need a graphical explanation, so here's the equilibrium constant. It's this red line. And if you have just a reaction at any given time, as the reaction is going here, shown this blue line, if Q is greater than K, the reaction is going to flow towards the left because it's too big and you're going to form more reactants. If Q is less than K, it's going to shift right to form more products. And this is just if you prefer the graphical representation of this. So, okay, let's do this for a problem. We have iodine and chlorine in equilibrium with 2 ICLs. So I guess iodine chloride. So, or it's iodine monochloride. Our reaction contains 0.114 atmospheres of iodine, 0.102 atmospheres of chlorine, and 0.355 atmospheres of iodine monochloride. Is the reaction at equilibrium? If not, which direction will the reaction proceed? Okay, so first of all, the reaction quotient at a given time is the products over the reactants raised to their power. So it's pressure or concentration. In this case, we're doing pressure of ICL squared. But I guess the delta N is 0, so the Kc and the Kp are in the same value, so it doesn't matter for this one. So pressure ICL squared over pressure I2 times pressure of Cl2. So that means our Qp is going to be 0.355 squared over 0.114, 0.102. What the heck is that? That's going to be 10.8. So let's see here, 10.8. Qp is too small. So it's, first of all, it's not equilibrium. So Qp is smaller than the Kp, which means we have too few products. So it's too small. So the top number needs to get bigger, and the bottom number gets smaller. That means we are going to shift right towards the products. Makes sense because 10.8 is less than 81.9, or Qp is less than Kp. So, which means top number is too small, bottom number is too big. The top number needs to get bigger, bottom numbers needs to get smaller, so we shift right towards the products. Question, yeah. Yeah, either one. But for this one though, because the delta N in moles of gases is 2, or I'm sorry, it's 0, it means they're actually the same. But the Kp and Kc are the same value for this one, because the change, do you remember we did that? Yeah. But yeah, it works for pressures or concentrations, just as long as you're consistent with which one you use. or in the rep case with this, but it doesn't matter.
It doesn't matter which kind of pressure.
No, it's all going to be relatively the same. Other questions? Okay. So, and now the next thing I'm trying to do is I'm going to try and to train you to kind of attacking problems. So like the other, like if you, well, many ways, I don't feel like I'm training you guys to be chemists. I'm training you more to think logically and problem solve. I don't think anyone here wants to be a chemist, do you? And that's okay. It's fine that you don't. There's very few chemists. Well, not very few, but we're certainly not the most popular major. But chemistry is a requirement, and 1/4 of all college students take general chemistry. And why do 1/4 of chemistry? Why do 1/4 of college students take chemistry? Because it's useful. It's useful, and I'm trying to, as I teach this, I'm thinking of your head and your careers, and one of the things I'm trying to do is also teach how to problem solve, at least attack problems. I guess I'm using violent language. Attack the problem and figure it out. So I'm showing you different types of problems and how to set them up. So here's a different type of problem, and so you got to be. I'm telling you how great the ice chart is. But sometimes it doesn't work, but it's a very good setup. But anyways, let's look at this one. So consider this reaction to whatever fluorinated phosgene. I don't know what the name of that would be. It would be carbon monoxide difluoride, but COF2, 2 CF2s in equilibrium with carbon dioxide and carbon tetrafluoride. Kc is 2. In the equilibrium mixture, the concentration of COF2 is 0.255 molar, and the concentration of CF4 is 0.118 molar. What is the equilibrium concentration of CO2? So this is one where if you write the ice chart, it's not going to work, because let's say you go ahead and do this. I like blue better. So COF2 equilibrium, CO2 plus CF4, and you go ICE, and you're given 0.255 and 0.118. You're like, what do I do now? I wrote the ice chart. Well, this is one where you just have to look at you don't need an ice chart. So Kc is 2. This equals concentration of carbon monoxide, CF4 all over COF2 squared. And you can look at it the other way around. From this problem, you have to figure out how to solve something. First of all, is this solvable? Actually, this is solvable. Because we have CF4, we have this, and we have this. So now what we have is one equation, one unknown. So 2 equals our X value. CF4 is 0.118 all over 0.255 squared. So of course, our X value, I like using X, I guess that's just from math, equals, it's going to be 2 times 0.255 squared. Right, I'm just rearranging it, rearranging the fraction there. And you plug in the numbers into your calculator, and this is it's going to be 1.10 molar. Okay. So again, oh geez, it turned yellow. Does it bug you if it screens yellow? I like pretty colors. So I know you said no, but okay. So here's another type of problem, and I told you how wonderful the ice chart is, but sometimes you don't need it. I mean, if you want, if you're just so used to writing an ice chart, you can go ahead and do it, but be careful with that. And then all you need though is the equilibrium constant arrangement, right? So products over reactants raise their power. So this is the equilibrium constant, and it's given to us as 2. And we don't know the carbon monoxide. We do know the carbon tetrafluoride, and we do know the COF2. So we put in those numbers, and then we rearrange for our unknown, and the unknown happens to be the concentration of carbon monoxide, and we get the value. So, do you guys know what a degree of freedom is? A degree of freedom. You ever heard that before? Okay. Yeah. So when you bind a system, you have to have the number of variables that you have has to equal the degrees of freedom that you have. So if you have too many degrees of freedom and you don't have control over one of them, then you have no control of the system. So meaning if let's say we had this problem, and instead of, let's say that we didn't know the concentration of carbon tetrafluoride, this problem would be impossible to solve. So because you would have 2 unknowns, you'd have 1 equation. Your number of unknowns has to equal the number of equations you have. And this is, there are physical reasons for this too. I mean, like when you're trying to control things, like position. So I used to be a laser spectroscopist. That's what I did for my PhD research. And you had to have the right number of mirrors around, depending on the laser table, in order to determine, like, if you wanted to control things. I had to control time and position. And so if you want to control position in 2 dimensions, X and Y, you need to have 2 mirrors on your table, at least. You can have more, but you need to have at least 2 mirrors on the table. One mirror to do X and Y. So although you could also do it by angle. So if you're trying to control angles, you have to do it by the number of angles that you have. You still would need 2, because then you'd have the angle kind of moving this way, another one moving that, well, I guess the radius and the phi, the sphere. I'm sorry, it's this one here and then this one here for spherical coordinates, if you're familiar with the spherical coordinate. Anyways, so, and if you didn't have 2 mirrors, then your laser pulse just flew around the room, which is dangerous because it can blind you, right? So, and you can't get any research done because your light's just going everywhere. So, I mean, there are physical effects to this too. It's not just math. So, but remember that you need to have the same number of equations as you do unknowns. So, that's just a math principle. But anyways, questions with this one?
I have a question.
Oh yeah, go. Is that Kiana? I didn't even know. Come on, go ahead. Yeah.
Wait, sorry, if you scroll up a little bit back to the problem.
Yeah.
That 2, that's coming. Oh, sorry. If you go like Kc equals 2, that 2, is it coming because there's 2 of the products versus reactants?
This is just the number. This is given information.
Oh, okay. Sorry.
Kc being, the question is, where did Kc equals 2? That's just given information.
Okay. Sorry. Thank you.
No, that's a good question. Proves my point about degrees of freedom. Thank you. Yes, please, Dennis. An equilibrium mixture. So Q is at any given time. Q is still, Q and K are the same number at equilibrium. Other questions?
Is it possible to repeat their questions when they ask one?
Okay.
Sorry, I can't hear anything.
I'm sorry, yeah.
And then I just hear the answer. I'm like,
Of course. Yeah, no, I guess I'm biased towards the physical audience and not so much the Zoom audience. I apologize. The question was, is this not QC because we just covered reaction quotient, but I circled the equilibrium mixture indicating that this is at equilibrium. So it's not QC and KC are the same thing at equilibrium. Do you understand what we're saying?
Thank you.
Yeah. Other questions? There were some questions. I'm inclined to wait 4 seconds. Okay, 4 seconds is over. Time to move on. Okay. Some more complicated problems. So I like teaching math too, alongside. I think some of the math theory is kind of cool. So anyways, let's look at this reaction. So nitrogen plus oxygen equilibrium with 2 nitrogen monoxides. Kc is 0.1. A reaction mixture initially contains 0.2 molar of nitrogen and oxygen. What is the equilibrium concentration of the reactants and products at this temperature? Okay, so let's do the ice chart. The ice chart is the best way to do it, in my opinion, for this one here. Initially, we're going to have 0.2 molar, and inferred 0. So if we have reactants, no products, and we are going to lose an extent of reaction of both the reactants, and we're going to gain 2 extent of reactions of the products. 2 because there's a 2 here. Or there's a 2 here, whatever. Okay, and then equilibrium, it's going to be 0.2 minus x, 0.2 minus x, and then 2x. So our Kc is going to be concentration of NO squared, concentration of N2, concentration of O2 equals 2x squared all over 0.2 minus x, 0.2 minus x. And this equals then, and it's given right here, 0.1 equals 2x squared over 0.2 minus x squared. So of course you can see where it's pretty easy to solve this one. We can take the square root of both sides. Square root of 0.1 equals 2x, or 0.2 minus x. Sorry, let me make it pretty. So that means 0.2 square root of 0.1 minus x square root of 0.1 equals 2x. Put the x's on the same side. 0.2 square root of 0.1 equals 2x plus square root of, or x square root of 0.1 equals x, 2 plus the square root of 0.1. And then that means then that x equals 0.2 square root of 0.1 divided by 2 plus square root of 0.1. And then put that in your calculator. And you throw that into your calculator and you get, is this the right problem? 0.027. And so that's our extent of reaction. And once the equilibrium, and the question is, find the equilibrium concentrations of reactants and products. So NO is going to be easy. So concentration of NO is just 2x, which is going to be 0.056. Is my math good? Oh, 4. Jeez. Why did I think 3? Then the concentration of N2 equals the concentration of O2. Oops. Equals 0.2 minus x. That's where I was getting my 3, I suppose. And It's going to be 0.173 molars. Okay, so let's say that we had tons of time left over and you're taking a test or you're working somewhere and you have all the time that you want. And you're like, okay, I'm going to check. You can check this. Your check is to look at your K. And it's going to be products 0.054 squared over 0.173. And if you do that, you get 0.097. And 0.097 is very close to 0.1. So you know that you did something right, that you're very, very close to since 0.097 is very close to 0.1, you know that you have done the right thing. Okay, so let me do a recap for this problem. So we have this equation, nitrogen plus oxygen makes 2NO, and we can then infer initially that we have 0.2 molar of the reactants, and then no, that's the given information, we have no products. So that means we shift right, so right Q is going to be 0. So products over reactants, we shift right. So which means we lose an extent of reaction of each of the reactants because there's no stoichiometric ratio, it's just 1. And then we gain 2 extent of reactants of products because there's a 2 in front of NO. And then we add the lines equilibrium value. It's going to be initial 0.2 molar minus the extent of reaction for both the nitrogen and oxygen, and then just twice the extent of reaction for nitrogen monoxide. We write the equilibrium expression, products over reactants. So it's going to be 2 squared over 0.2 minus x squared. That given is equal to 0.1. So we take the square root of both sides and we solve for x. And then to be doubly sure, we put in a check to see that if we actually got the right answer, and it turns out we did. And is there a step here that you could maybe argue that I did wrong? Why couldn't this be plus or minus? Right, you take the square root. I could have plus or minus in that one, right? So that's the difference between math and the real world. So one thing you have to understand, math is a model. It's a very, very good model, but it's a model. Models aren't real. So there is no plus and minus in the real world. There is no such thing as a negative concentration. So you can get rid of the positive. You can get rid of the negative roots. So from that, though, does anybody know the fundamental theorem of algebra? No one's ever heard of that. Fundamental theorem of algebra means x to the n has n roots. Do you know what a root is? A root is when the function crosses the x-axis. This function here has 4 roots. So it's 4 places where the function crosses the x. Some of them could be double or triple roots, but it looks like it's 4, right? So the number, when you have a polynomial raised to some power, that polynomial then has the whatever power it's raised to, as long as n is a whole number, it has that number of roots. So, which means, mathematically speaking, you will have that many solutions to the equation. The thing is, though, that when you try to apply it to something that's real and physical, only one root actually works. So this one's easy in a way because it's a square, and because you square something, mathematically speaking, you generate another root. But this one's easy because it's concentration. You throw out the negative root. It's kind of duh. It's easy. So here's one that's a little harder. So And this is, I got to keep my thinking game on because this is a hard problem. Okay. So consider this reaction, N2O4 in equilibrium of two NO2s. Kc is 0.36. The reaction mixture initially contains 0.1 molar. What are the equilibrium concentrations of NO2 and N2O4? So, oops, this is a 2 here. So initially, so let's see here. So this is 0, and then this is 0.1. So we have 0 and 0.1. And that means that we're going to shift left towards the reactants. So that means we're going to have one extent of reaction, and we're going to lose two extents of reaction there. Equilibrium, we have x. And we have like 0.1 minus 2x. I guess I don't need the parentheses. So our K, EQ, is going to be NO2 squared all over N2O4. Oops. That's a 4. Equals, oops. It's going to be 0.1 minus 2x squared over x equals 0.36. And this is one of those, oh crud, time to do the quadratic equation. So 0.36x equals 0.1 minus 2x squared. Do you guys know how to do, you guys ever heard of, I'm sorry, I keep on giving you like all these math things to remember. You ever heard of Pascal's triangle before? Pascal's triangle is this: 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. You add these, so you put ones on the side, then you add the middle one. So for this line, well, for this first line, it's 1 and 1, and then you put 1 on the outside, then you add these two numbers to form 2, and then 1 on the outside. Then you put 1 on the outside, then you add these two numbers to make 3, you add these two numbers to make 3, 1 on the outside, you add these two numbers to make 4, you add these two numbers to make 6. So this is known as Pascal's triangle. Did you guys learn this in algebra, at least as far as polynomials and how to, like when you have them to a power, to FOIL them quickly? But you can use for a squared, and if you can use that line there, the 1, 2, 1. So this is 0.01, the first one squared, times 2 times the middle. So it's going to be minus 0.4x plus 4x squared. So if you FOIL that one there, you can do that. And you can also you can subtract 0.36 from both sides, and you can have, so let me write it this way, 4x squared minus 0.76x plus 0.01 equals 0. So of course, this is the a squared plus bx plus c equals 0 from algebra. And let me make sure I'm getting my math done right. Okay, good. I got it right. I just don't want to make any mistake. So I'm looking in the book to make sure I'm doing the setup correctly. Okay, so now you have this, you can apply the quadratic equation. And that means that your unknown is equal to negative b. So it's 0.76 plus or minus the square root of b squared, 0.76. I know it's negative 0.76, but squared gets rid of it anyways. Minus 4, a is 4, c is 0.01, all over 8. Oops. 2 times 4 is 8. So you do that. And I'm going to skip ahead. X equals 0.176 or 0.014. Okay, so this is where you have to then look at one of the answers and figure out which one is real and which one is not. And the real answer, and you look for a physical malady. So something that's impossible. This is the real answer right here. Because if you look at this line here, so equilibrium value of NO2 is 0.1 minus 2x. So 0.176, you double that, that's going to be about 0.3. 0.1 minus 0.3, you get negative 2 something. Or it's a negative 0.2. Either way, if you use, I'll change colors. If you use this root, this results in a negative concentration of NO2. And there is no such thing as a negative concentration. So no such thing as a negative concentration. Therefore, that one is wrong. You have to throw that one out, and you can only use the x equals 0.014. So, and the problem is find the equilibrium concentrations of NO2 and N2O4. So we have the extent of reaction. And then the equilibrium value, so concentration, let me change back to, I'll do calming green. So this is our answer. Concentration of N2O4 is equal to X equals 0.014 molar. And then concentration of NO2 is equal to 0.1 minus 2x equals, so 28, maybe 72, 0.07. .72 molar. And then we can go ahead and check it. So our check, it's going to be, so concentration of NO2 squared, wait, no, that's products over reactants, N2O4, 0.072 squared over 0.014. If we do that, we get 0.37, which is the original answer popped out. Okay, so how much time do we have? I'm not gonna go, unless you want me to. If you explore this and you get 0.17, so you get that negative 0.3 something. If you have the negative 0.3 in the equilibrium constant, when it squares it, it turns it positive. So that number will generate 0.37. But again, then again, the 0.37, that's just a math trick. It's not the, it's a breakdown of the fact that math has failed us. Math as a model. And the physical reality is there's only one answer to this equation. This equation being this one here. It's 0.14. So because we have a physical whatever fallacy, and that being a negative concentration. But okay, let me go back and repeat this one. So consider this equation. N2O4 in equilibrium with 2NO2. Kc value is 0.36. Initially, we start with 0.1 molar of NO2 products. What is going to be our equilibrium value of the reactants and products? So we're given products and no reactants, so we shift left towards the reactants, and we have a X extent of reaction left the product, and we lose 2 extent of reactions from the, we gain extent of reaction, 1 extent of reaction to the reactants, and we lose 2 extent of reactants from the products because there's a 2 here. And then we're given the equilibrium values, X for the reactant, 0.1 minus 2X, extent of reaction for the products. We put that into equilibrium expression, products over reactants, and we get this expression here. We FOIL it and solve for 0. And then we apply the quadratic equation, and you get 2 roots. So the 2 roots, one is real, one is not. And using our amazing, beautiful minds, we determined that one of the values will give us a negative concentration for the NO2. So we throw that root out and we keep the smaller root. And then we plug in the numbers and we figure out then that the equilibrium concentrations for the reactants and products are listed there. And we even went further and checked it to make sure we're right, and it turned out we're right. So, questions with this? Again, this is just from the fact x to the n has n roots. And mathematically it works out, but real world, and I mean chemistry in terms of the real world, funny, I'm calling this here in academia the real world. When you apply it to the real world, then the mathematical model breaks down, and you have to pick one. And that's the one you pick. You pick the one that doesn't cause a physical, whatever, fallacy. So I remember when I was a student, that was one of those, oh crud moments. So now I have to look at the equations and figure things out. As I get older, I'm like, that's really cool. As I kind of went through and I said, this is what math is. Oh, math is a model. Oh, and you know, we have to apply the model and we have to make the model work for us. So, and as it stands right now, it's also furthering some things. Computers can't do this logic. So only humans can do this logic. So right now we don't have any, we don't really have that much of an AI. I guess we more have machine learning is where most of our stuff is done. We don't really have artificial intelligence yet. We only have biological intelligences like us. But we humans are the only ones that kind of can think this way so far. So it's right now it's a uniquely human trait. Maybe that'll change in the future. But one day, yeah, kind of scary. So I mean, you know, the CAPTCHA or whatever it's called, they're Turing. You know what a Turing test is? Yeah. A Turing test is, so, well, the Turing principle, like kind of test is if a human cannot tell if a computer is another human or another computer, then the computers have won, kind of thing. But right now, there are things that humans can do extremely well and quickly that computers have a really hard time doing. And one of them is recognizing patterns. So humans are really great at that. So I mean, like trying to find smiley faces, for instance. Humans find smiley faces everywhere. You know, we think that the plugs are smiling at us sometimes. You know, that's I mean, like when you do those the CAPTCHA, they're Turing tests. They're trying to figure out if it's a computer or not. And like when they say like find the crosswalks, find the bikes. You know, like a human can tell the difference between a bike and a car like that kind of thing. So, but you what? It could be. They're like some of them are simple. My wife one time was she wrote a program to try and recognize pandas, because pandas have she was looking at the eyes because there's the black circles and so like and she was seeing like the shadows and things. Sometimes the computer would think that shadows were pandas, you know, whereas a human like that's not a panda, that's just a shadow, you know, kind of thing. So it's even still, they're getting better. I mean, maybe you're right, they're getting better, but humans, it's something we do effortlessly. So, but this is one thing, this determining, applying math to the real world. This is something that humans can do, not necessarily effortlessly, but maybe in the future, we'll do that. That's the other reason why, if you're wondering why I'm like, wow, I let you do everything in chemistry class. I mean, when you're taking the test, you have your calculator, you have your phone, you have Google. Computers can't solve math, can't solve chemistry problems. I mean, they can, but you can only program a computer to solve a specific type of problem. We humans are the only ones that can logic our way through each and every problem. And that's also my teaching method, is I'm trying to give you the overall picture of this so that you can logic your way through all these problems. So, but anyways, any questions with this one? Sorry for all the philosophy of math and also where we're going in society. Anyways, let's look at the next problem. And this is where things get a little easier. So things can get a little easier, and you will see some of this quite a bit, especially in the next chapter. So let's look at this equation here. So 2 hydrogen sulfides in equilibrium with 2 hydrogens and sulfur. And the equilibrium constant is 1.67 times 10⁻⁷. And a half-liter reaction vessel, the vessel initially contains 0.0125 moles of hydrogen sulfide. So what you want to find are the equilibrium concentrations of the products. So the initial concentration of the reactant, it's just double the value because it's a half molar. So moles per liter. So 0.0125 divided by 0.5 liters, it's just 0.025 molar. So initially we have 0.025 molar, 5 molar of hydrogen sulfide, which implies no reactants, I'm sorry, no products. And now we shift right 2x, we gain 2x here and x here, plus x here. Oh, actually, sorry, I wanted to go back. Another way you could solve this problem, I'm sorry, if you turn back to this one, you could call this x and call this one x over 2. So it's up to you, the biological intelligence solving this problem. It's up to you the way that you describe the variables. I prefer not using fractions. I like multiplying better than dividing. That's me personally. If you want, you could call the extent of a reaction x and that one there, and then call the extent of reaction for the reactant side x over 2. That works fine. I don't like that. I prefer multiplication over division, but it's however you, the user, wants to do it. But anyways, let me go back to this one. Sorry for the aside. So again, we could call this one minus x plus x over 2. But I don't like that. I prefer the bigger number. I prefer multiplication over division. So, all right, so equilibrium value here, you have the 2 lines. So it's gonna be 0.025 minus 2x, and x. So then our equilibrium value is, I'm going to go ahead and 1.67 times 10⁻⁷ equals products 2x squared x 0.025 minus 2x quantity squared. Now this looks horrible. This is one of those So, right, of course, when you're doing this, what is this going to equal? This is going to be 4x cubed all over. You have to FOIL that one out. It's going to be minus 4x squared plus 0, 5 minus 0.05x plus whatever 0.025 squared is. That's right. So we have to divide the polynomial. That's going to be a horrible thing. Can you imagine if your math test, the teacher gave that as the problem to do? This is when you want to start throwing things at the teacher, right? So there is a way, there is a shortcut. The shortcut here is where you can approximate. This is, instead of equal sign, I'm just trying to use approximate this. You can look at this right here, and you can say the x is small. So I can say, you know what? This x value is really small because if you look at the equilibrium constant, that's a small number, right? So remember when we talked about, so 7 to the minus 7, so that's 10 millionth, right? So this is 1/10 millionth. That means this reaction goes forward by a factor of like 1/10 millionth-ish. So, and compare 1/10 millionth to 0.25. What I'm saying is this reaction doesn't go forward very far. So we can say this is approximately equal to 4x cubed all over 0.025. So I'm just saying that, and we can talk about it much more later if you're uncomfortable with this. A lot of students are uncomfortable with this, by the way. We can look at this and say, you know what, this number here, it would make my life easier if that x went away. So I'm just going to pretend like it's not there and approximate it and say, you know what, the extended reaction is not going to be very far. And I'm just going to say it's not there. And then I'm going to discount it. And then our math becomes much easier, right? So it's going to be 0.025 times 1.67 times 10 to the minus 7 equals 4x cubed. So divide both sides by 4 and take the cube root of it. So you get x, and then we throw it in our calculators. And we get 2.97 times 10 to the minus 4 is the extent of reaction. Okay. And then the next step is the equilibrium. That means, so it just wants the concentration of the products, right? The concentration of equilibrium concentration of H2S2. So concentration of H2 is going to be 2x, which is going to be 5.94 times 10 to the minus 4. Is that right? Oh, next page. Yep, that's right. Concentration of S2 is just going to be x, 2.97 times 10 to the minus 4. Okay, and we're done. Okay, so let's look at a couple of things though for this one. And again, students have a hard time with this, is which S to discount, which ones not to. But so, well, Kiana here, I guess. I'm going to talk loudly so Kiana can hear me. So, and Kiana, I'm pointed towards the minus 0.2x right here. So with this problem, we're making an approximation. We're saying that this bottom number right here is approximately equal to 0.25. So that's the stretch there. So, and this is, I said it's approximation. And this is something that we did before we had, you know, awesome frickin' computers that were also, you know, cameras. And when I was going to school, we had graphing calculators. If you have your graphing calculator and you have the solver function on it, just use it, right? You guys, do you know how to use those things? Do you know use like the graphing calculators and or using MATLAB or Mathematica, those kind of things? If you want to, you don't have to do the X is small. You can just go ahead and get use the solver function and get the right answer. You know, it's even the better answer. The other thing is to what degree, and this textbook, this says if it's within 5%, the discounting is okay. So like if this value is within 5%, this is okay. And so meaning if we get this value, so if you take 2.97 times 10 to the minus 4, we divide it by 0.025. If we do this, it's like 1%, a little less than 1%. Yeah, it's one point, so it's going to be 0.001, not too many zeros. 0.119 or 1.19%. And that means it's kind of like by taking this approximation, we're introducing about a 1% error into our calculation. And we're saying, you know what, that's okay. So one of the things about being a scientist is, and especially an engineer, is that you have to be able to manage your error. And quite frequently, the measurement that you have, like probably the pressure instrument probably has a 5%-ish error anyways, depending on how good your pressure sensor is. So you're like, all right, well, that's okay, kind of thing. So, and I said managing the error. So you have to look at your application. So when you're managing your error, you have to look at the application. If you are, some of those space probes are incredible. This is the Deep Impact Probe, where they launched a rocket that shot another rocket at a comet and hit the comet, and to see what was on the inside of the comet. Can you imagine the calculations that must have gone into that? So like, I mean, it's just insane, right? Because you had to get the rocket up in the right position. And then after you're in the right position, you had to plan it out, but then, you know, you had to make sure it was pointed the right direction, and you had to shoot something, you know, across millions of miles or tens of millions of miles to hit another object, you know, like the size of this room, right? With you know, with something like as big as this water bottle across 10 million miles or longer. I don't know how many millions of miles it was to hit something else that's moving at 20 miles a second. You know, can you imagine how tight your calculations are for that? That's one thing where 1% error is not acceptable, right? 1% error in the Deep Impact Probe, that's not acceptable. For something like this, it's fine if you're worried about the pH of if you're at a Coca-Cola manufacturing plant and you're worried about the pH of your Coca-Cola and it's off by, the acid level is off by 2%. Does that mean you're going to reject the batch of Coca-Cola? The answer is no. No one's going to notice, right? So it's one of those, it depends on what your application is, how good your error is, or how close you want your error. And there are many equations and many relationships. If you go and study on heat transfer, a lot of things are discounted in heat transfer, a lot of terms. Even the famous equation E equals mc squared, that has X is small approximation in that too. So there's lots of equations that you see that just outright discount these values. So, and again, I'm sure this is one of those like, and I oftentimes I get students and it's later on like, okay, which X can I discount? And one of the questions I get a lot of times from students are, why can't I discount these X's? And the reason is you can't discount these X's because this one here relates it to another number. You're relating this X, this minus 2X to 0.025. Okay, so what you're saying is 0.025 with a very small x is approximately 0.025. If you say x up here, x, like, okay, well, why can't I just discount this and say x is 0? Well, then if you do that, so let's say you put the top number as 0 as well, what you're saying is 1.67. So this number becomes 0, the numerator becomes 0, times 10 to the minus 7 is approximately 0. And this is a true statement, right? 1/10 millionth is approximately 0, but that doesn't get us anywhere, right? So we are trying to solve a problem and get real values. And right, so if I, and the answer is, 0.003, I'm sorry, well, 3 times 10 to the minus 4. So if you say, well, what is the value of the products? And you say, oh, it's approximately 0. I'm like, well, yeah, I know, but I still need to know the number, kind of thing. So if you put 0 in for this top number here, then that just tells you that gets rid of any, it takes away the degrees of freedom, and you get a fallacy. You get an answer, but it's like a fallacy sort of answer, meaning like this number here is approximately equal 0. I mean, that's true, but it doesn't get us any usable information. The point of discounting this X here is that so that we can extract usable information from this by introducing a little bit of error and making things easier for us. And again, this may be outdated because we have sweet computers now that does all this stuff for us, but the general chemistry was kind of, I don't know, been taught the same way since 1960. And so we kind of teach it the same way, and we still teach it the same way. But we also have a lot of equations that use these X's small. So that's the reason why we haven't gotten rid of it yet. Okay, so I know there's 2 minutes left. So same idea, initial change equilibrium, we're given an initial concentration of reactant. We lose 2 extended reactions of reactants. We gain 2 for hydrogen, 1 for sulfur products. We write the equilibrium expression, and we do a trick where we discount the reactant, extended reaction for the reactants to say that the products over the initial concentration of reactants is equal to the equilibrium constant. And we get the extended reaction, which is within about 1% of the original value, so that's fine. And we think 5% is or 1 out of 20-ish is okay. And then we just use the 2 extended reactions for hydrogen and 1 extended reaction for sulfur, and we list that as our values of our products, and it'll be within 1-ish% accurate. So, any last questions for the last minute of class? Nope. Okay. Like I said, I know I told you Chem 162 is easier, but here I am throwing you all these new concepts. This is probably a rough day for you today. So hopefully it's not too bad, but